All right, our next speaker is Michael Tingley. He'll be talking about probabilistic programming at Facebook.
Good morning, everyone. Thank you for taking the time. Looking forward to meeting you all outside of the actual presentation format here. Just wanted to share a little bit of what's going on in the probabilistic programming languages space at Facebook. So I'm part of the probabilistic programming languages team here. Some of the team members are in the audience too. I encourage you to say hi. So today I'm just going to go over a few quick sections here. So motivation, what we're doing, high level kind of background where things are coming from, a bit about the framework that we're building out for probabilistic programming, and then just a really quick touch on a couple applications that we've looked into so far. So starting off with the motivation. So it all started with the leader of our org, Eric Meyer. So back in February of 2017, he published an article in the ACMQ, Making Money Using Math, that really gave a kind of a high-level overview of, what are the kind of processes that go into businesses nowadays, and sort of how are they being used to monetize different processes, and then really thinking about, many years into the future, like how can we automate some of these processes without actually like encoding the different kind of decisions that are made, but really do the online learning. And so kind of what he came to was, we have a lot of tools in our disposal, but if we're thinking into the future, what this is probably going to look like is something along the lines of a higher level language where people are encoding this kind of uncertainty, these uncertain choices, rather than encoding in heuristics. And so what Eric arrived at was that we should start investing in that, not only as a company, but as an industry. And what this meant was looking into probabilistic programming. And so our take on it was, what can we do to make probabilistic programming languages accessible to everyone at the company? We're very, very early in this kind of mission here, but it's one that we want to keep continuing down the route. And so at the sort of mid to late 2017, we formed the probabilistic programming languages team to just sort of explore this space and understand how we could use it to advance the technologies at Facebook. So for better or worse, one of the languages that's most used at Facebook is Hack. It's a language we've developed in-house. It's our server-side language, originally based in PHP. And so one of the goals, if we want to make a language accessible to everyone here, is to really come to the developers where they're standing. And so we approach this with the mentality of, since we have so much control over this language stack, let's extend it. Let's see what we can do. And so that's sort of where we've come from here. You kind of get, just taking a look at kind of the development cycle here, developers, when they're working with this, have a very fast turnaround cycle. This is the biggest selling point for Hack. They have a sort of a snappy response, a quick iteration time. They make an edit in their IDE, they click refresh, and the change is immediately viewable in their browser. When designing the PPL technologies that we wanted to look into at Facebook, we wanted to keep this philosophy to help developers have this fast kind of iteration cycle. So a lot of the kind of things that went into our thoughts are actually similar kind of to how Web People was originally designed, sort of with this very sort of iterative style of development, where you can kind of change a model. There's no compilation process really necessary, and you can kind of see the results incrementally. So we set about to build something that would help developers within Facebook in a similar way here. So I'm going to go into a little bit of our language, Hack PPL. So just a real quick sneak preview here. This isn't the final code here or anything, but it helps paint a picture that kind of what we're trying to build here, and this is just a really basic univariate linear regression, by the way, that you can have a language that feels just really well integrated with an existing language by just like being smart about building out the sort of modular components that go into here. And so actually all of the code here really just feels and integrates well with Hack. Even from this slide, the only real visible extensions that we've introduced were sort of coroutines, this suspend keyword. Everything else is sort of ordinary Hack. You can use imperative constructs, for loops, arbitrary calls, everything that developers are used to here. And we've got, obviously, the probabilistic constructs here for sample and observe. So we'll take a look at this in a few slides as well. So when we're thinking about extending our language to support probabilistic programming, these are sort of some of the areas that I divide my mental model into. And so we're going to sort of work from the bottom up real fast here. So coroutines, this was one of the first things we extended with our language. Coroutines, in case you're not familiar, are a programming language concept that they can mean a lot of things. For the purposes of this talk, we can think of it as a function that can be paused and resumed partway through its execution. And we've implemented a variant for multi-shot coroutines, which allows you to resume multiple times. So in terms of probabilistic inference, what this means is that we can pause the inference partway through and then breed additional threads or additional traces that let us selectively explore the posterior space. And at the bottom is just an extremely basic example of how you could imagine like a coin flip example. It's pretty much the simplest thing you can have. It's pretty easy to imagine how you can pause at each of these spaces and hypothesize what would happen if I flipped heads, what would happen if I flipped tails. So in a discrete case, fairly obvious. For a continuous case, you're not obviously exhausting all possible choices, but it gives you that mechanic to sort of explore the surface. Another extension that we've implemented was reactivity for hack. So there's a couple things that go into this. The first is purity guarantees. So we offer guarantees for effective purity, which would mean that outside of the scope of an individual function, you can't bleed impure semantics. You can't sort of store state or rely on external state that would be observable. This is really useful for ensuring that the developer, since we're integrating into this existing language that has a lot of sort of imperative constructs in it, this offers a mechanism where we can lock down and make sure that whatever the user is doing isn't going to break their inference by sort of containing assumptions that are not consistent across each run of your model during inference time. And then another thing that it can offer is automatic caching for results. And so in certain kinds of models, like Dirichlet-Process kind of models, like this can be very useful for just making the language, making the modeling just a lot easier to write. And a note, so some of these things are not completely integrated with PPL, but at this point in time. But the big thing I want to say here is that by integrating in this sort of existing language, we're able to offer benefits across the entire language spectrum and that are not just contained to PPL users. They're really just general language features that also happen to be useful for PPL as well as other language features outside. So if you guys are familiar with PyTorch, you might have heard of A10. So A10 is the Tensor's core running in PyTorch. So of course, since we're building on a language on top of PHP, performance is not an easy thing for us. However, this lets us sort of break that limitation, really get into sort of a multi-threaded environment where we can perform fast and scalable tensor arithmetic. Compared to a vanilla implementation in PHP, we see orders of magnitude and asymptotic speedups. That really this is the core of how we're going to be able to address any sort of non-trivially sized problems. It's also got the nice familiar NumPy-like ergonomics for that's much more amenable to the way that data scientists are conditioned to think. And it's also hosts AutoGrad. It's continually being upgraded, so we get a lot of free wins here. Again, not only for HackPPL, but if other folks are interested in using tensors, that's a general across the world win for us. As far as our HackPPL library goes, it's got sort of all of the mainstays of modern PPLs at this point. We've got all of your sort of standard inference methods, HMC, variational, sequential, the list goes on. I'm sure folks in this room are familiar, so I'm not going to sort of dwell on this. We've got the change of basis transformations that let us perform gradient ascent in an unconstrained space. We have a very large repository of distributions and statistical tools. Some of these currently are built on top of A10, and we're working with the team there to integrate more of their distributions as part of their tensors framework that will hopefully also improve the life for folks that are sort of built on top of PyTorch. In terms of diagnostics, like we're trying to provide a very responsive experience to the user where the diagnostics are sort of applied somewhat automatically where possible. The users get immediate feedback about the performance of their model and we can calibrate it as they go. Rather than sort of waiting for the compile and inference run to complete, we can kind of give early signals about what it looks like is happening. just moving on here. So I want to go back to the modeling language that we'd seen a few slides earlier. So with some of these additional concepts baked in now, we can improve on this. So with just a few extra lines of code, we've now sort of integrated tensors into the library. It gives us a big speed up here in terms of performance, but it also makes it really easy to express, to take things into arbitrarily higher dimensions. Sort of exploring the multivariate use case is trivially extension from this. Another thing that I want to call out, in the previous slide, you saw your observations were coupled into your model, so we pull those out, and we now allow you to sort of condition after the fact. It also allows us to run predictions, PPCs, diagnostics, in a much more generic and automated kind of way to give information back to the user as early as possible without them having to rework their model to capture these concepts. Our team's introduced some additional language features to make just the writing experience for the model easier. So there's no more coroutines anywhere in here. There's also a state accumulator, which I didn't show anywhere in here in the previous slides, but originally the user would have to write that. We can do away with all of that with just some sort of smart PL kind of rewriting. Obviously, there's still a long way to go for us in terms of getting a smooth modeling experience. The tensors here are very verbose. We have sort of IDs all over the place. There's a lot that we're currently working on to simplify this and also provide better static guarantees through better static type checking for tensors. Lastly, since we own the whole sort of software stack within Facebook, it gives us the freedom to really think about what's the user experience for these models. So when we're targeting data scientists, how do we give them the best possible feel right out of the gate? And so we are able to integrate directly into the IDE that folks use. It's called Nuclide, and when you open a PPL model, we'll detect that, immediately pop open the results, pop open the pane that lets you sort of run, debug, visualize your model all right there. It's highly interactive using sort of plotly graphs. And in the last few minutes here, I'm going to go into some applications that we're using this for. So as we're still a pretty new team, we're focusing on definitely the sort of low-hanging fruit at this point. So one of the cases that we've explored is ads lift. Ads lift is a metric for determining how effective one ad is versus another. So advertisers will typically run a test and a control ad, and they want to learn if the test ad is more effective, and if so, how effective. So the pre-existing way that was being done was kind of interesting. So observations of the ad's revenue would be observed, and they would use a multinomial sort of binning process to bootstrap replicates and measure the uncertainty in that ad's lift. And then, so there's sort of a few weird things going on here. Definitely the binning process is somewhat arbitrary in my opinion. And it also makes it quite difficult to interpret the final results, what exactly is being measured. So what our team has done is we've come in here with a very simple model for the ads lift folks, and we can just model sort of a slightly hierarchical model here where we model did a user convert, so did they end up interacting or clicking on an ad, and then given that they've converted, what does the distribution for revenue look like there? And this lets us really just directly model the situation. And I can't really share the actual performance improvements here, but I can give the high-level takeaways is that in addition to directly modeling and providing interpretable results, this now lets us sort of explicitly model latent variables of interest. So one particular thing in the example that I've shown here, the conversion rate is now something that advertisers can sort of be measured as a specific thing with uncertainty, and we can present that when trying to provide insights. So very briefly, another problem that I want to touch on here, measuring fake account prevalence. So fake accounts within Facebook, the vast majority of our accounts are genuine users. Some of them are not. We call these fake accounts. And so we have a number of reviewers here which look at accounts and evaluate whether they're fake or not. And they report this up, and then we take action based on those reviews. So in the happy path, the majority of reviewers for a given account correctly identify the label. And so you'll see here that if the account is actually fake, and enough reviewers label it as fake, we will consider the account to be fake and take action on it to measure the uncertainty in this process. Again, the fake accounts team uses the sort of true false, the false positive and false negative rates in order to bootstrap a number of accounts and measure sort of how often we're getting things right, how often we're getting things wrong, and apply that to the full population. Unfortunately, if the majority of labelers, reviewers don't accurately identify the account, we get the process wrong. And so what this means at the end of the day is we will still do bootstrapping off of an example like this, where the majority of labelers said the wrong thing. And the bootstrapping results will be systematically biased. So we've come in instead and offered a probabilistic programming language to directly model the situation. And so we have some true prevalence rate underlying, which is a generative process for accounts that are either fake or not fake. And then we also have some error rates, which are used by our reviewers and applied to individual accounts to say, oh, this account is fake, this account is not fake. And now with this generative process, it's very easy to imagine how you condition data on it to actually measure not only the actual account, the prevalence rate, but also interesting other latents like the error rates, which let us take action not only on reporting at fakeness, but also work with the reviewers to try to reduce these error rates. Yeah, and so I'm running out of time here, so I'm not going to dwell too much on this. But kind of the big takeaway between all of these things for me is that by using probabilistic programming, we get rid of these somewhat more ad hoc approaches and replace them with sort of principled generative stories that everybody can sort of understand in the same way. Like there is one interpretation of what this means versus some of the bootstrapping processes are kind of somewhat arbitrary. And not only that, but this lets us report latent variables that are often in their own sense like very actionable from the company's perspective. So this is just a touch on the iceberg, but it's where we're planning to go with everything, and I appreciate your time here. Thank you.
So we have time for a couple of questions. Any questions in the audience? Way back there.
I believe the question was how do we compare A10 and Pyro? So I think they're somewhat different categories of things. So A10 is a tensors library that lets us sort of do the fast maths. And so A10 actually, the core that we're integrating with is actually in C++. And so we use as an extension the PHP code that we write on the top sort of hooks into this for the runtime. Pyro, on the other hand, is written in Python, and it's used for probabilistic inference. So I'm not sure if I totally understand. Is there a particular thing I could answer more?
Okay, I saw another hand way at the back, or did I miss that? Oh, a question over there, yes.
Did you design the structure of, so in the fake review example, did you design the structure of the model yourself by hand, or did you actually try to learn it?
We did design it by hand. We worked with some folks on that team to try to figure out what exactly are the insights that they're trying to learn here. Definitely one of the interesting challenges at Facebook is we think that probabilistic programming is a very powerful tool to apply to lots of common problems, but the vast majority of folks at the company aren't aware of it. So working directly with these customers helps not only helps those teams learn about it, but helps us get a sense for the kind of models that folks are trying to build out here.
Okay, thank you very much.
Thank you.